In 4.8 Day 2, we are going to continue to work on applications of trigonometry, and simple harmonic motion is one of those applications. So simple harmonic motion is a type of motion that involves either a sine graph or a cosine graph. Now you'll notice here that there is a different variable being used, a couple different variables. There's omega, the little W looking thing for the coefficient, and then t is the x value, d is the y variable. They're different variables, but they all pretty much mean the same thing as what we've been working with, so we really don't need to worry too much about it. If you want to go back to the traditional variables, that's fine too. But we're going to be, when we talk about simple harmonic motion, there are going to be two things that we focus mainly on, and that is period and frequency. Now in last unit, we kind of glossed over frequency and said we'll talk about that later. Here's the later. So period is as we know, you just take whatever the coefficient is in front of the t variable or the x variable, and you just divide 2 pi divided by that coefficient. So that's period. We've done a lot of that. Frequency is just simply the reciprocal of period. So I wouldn't do a whole lot with frequency other than just know that it's the reciprocal of period. That's really as much as you will need to know about this. Frequency, period is how much, basically is the amount of time it takes to do one full cycle. Frequency is number of cycles per unit of time, and so it's just the reciprocal. It's nothing crazy there. One thing about these, when we're doing simple harmonic motion equations, we need to decide between sine or cosine of that equation when we write this equation, depending on the displacement at time t. Basically, displacement means where is it at time t equals 0. So remembering that if the point that we have is 0, 0, then we're most likely dealing with a sine graph. And if we're doing something with 0, 1, or maybe 0 maximum, it doesn't matter, it doesn't necessarily have to be 1, then we're probably talking about cosine. And in a lot of cases, the harmonic motion graphs will tend to be cosine because we have to get them started in some spot. So we'll see that here in a second. We've got an example, first of all, of this harmonic motion. So here is an example of this very thing with the motion of a spring. So I've got this picture down here, and I just want you to imagine this is where it's just hanging at equilibrium. You pull it down to this spot right here, and then you let it go, and then it oscillates back and forth. And so we want to know how to find an equation for that. So it says, consider a mass oscillating up and down at the bottom of a spring. The weight is displaced at a maximum of 5 centimeters. It takes 4 seconds to complete one full cycle. So 4 seconds for one full cycle, that means period. So if we want to know the frequency, so the period is equal to 4 seconds per cycle. The frequency is just a reciprocal of that, so that is going to be 1/4 of a cycle per second. So I would always just take a look at what is the period, flip it over to find the frequency. And there will be a problem just like that on the test where all you'll have to do is take the period and flip it over. Okay. Now find omega. If we're going to be looking at the period or the frequency, I tend to like to go back to period more or less, and that is, period is 2 pi divided by omega. We need to find out what that coefficient is. We know what the period is, so what we might want to do here is just say 2 pi divided by that variable equals 4. And then we can solve this for omega, for that variable. And so that's going to be, if we if we maybe multiply by omega on both sides and get 4 times omega, divide by 4, so then 2 pi divided by 4 is going to be our coefficient, which reduces down to pi over 2. And so we're finding this in order to write the equation. which is part C. Find the equation at if the weight is at a position of -5 centimeters at a time t equals 0. So in other words, we pull it down to -5, let it go. So -5 is the starting point. Now if that's the starting point, that has something to do with what I was mentioning, how cosine starts somewhere other than 0, 0. In this case, it's starting at -5. So that means if we're looking at our formula here, I'm going to go y, you could put d, that's fine if you want to do d, but I'm going to use y, equals -5 cosine. So that'll start it down here at -5, and then it'll go from there. And then we found that the coefficient is pi over 2, so that's going to be what goes in front of t in this case. So this is our equation. We found the coefficient based on the period or the frequency, however you want to do it. And then this -5 is where it started, so that means it's an amplitude of 5. We take it down to -5, but then it's cosine because that's where it starts after we start going back and forth with that. So this is one example of simple harmonic motion, a spring going back and forth, and we'll have one or two more before the end of this section.